Hi, welcome to BC Video 9.7b Part 2, Taylor Polynomials. All right, Maclaurin's, still same thing. Now I'm just writing it with a summation notation. So summation I goes from 0 to n being the degree of the polynomial. Okay, and this is Maclaurin, so it's near 0. So that's just writing in its shorthand form. Now, a Taylor polynomial is now going to be near c, which c could be any constant. It could be 0, could be 3, could be 2, could be 5. So we're going to call this a Taylor polynomial. N is the degree. It's the same exact formula as we had up here. The only difference is instead of taking the various derivatives at 0, you're going to take the various derivatives at c. And also, instead of it just being x to a power of I, it's going to be x minus c to a power of I. But otherwise, the same idea. Okay. So, so here's a Taylor. So what the Taylor would look like this right here. So we already saw this. This is Maclaurin's. So it would be f of c plus f prime of c times x minus c plus the second derivative at c over 2 factorial x minus c squared plus the third derivative at c over 3 factorial times x minus c cubed, etc., until you got to the nth term, because we are talking a polynomial of degree n. That would be the nth derivative at c over n factorial times x minus c to the n. Okay, so if you look at the book, numbers 25 through 30, it says find the nth Taylor polynomial centered at c, whereas 13 through 24 say find the Maclaurin polynomial of degree n. So notice here they don't give you a c because Maclaurin's implies that c is 0, whereas here they have to give you the value c. Okay. All right, so if we look at 20, this is like 26. F of x they give you is 2x squared. They want a polynomial of degree 4, and they want it to be a Taylor polynomial because it's near x equals 2. Okay. All right, so we make up our table. We start at 0. We go till we get to 4. We have the nth derivative at x, and then in this case, the nth derivative at 2 because it's a Taylor, not a Maclaurin's. Okay, so the original function is 2x to the negative 2. Take the derivative, take the derivative, take the derivative, take the derivative. Notice I'm leaving all negative exponents because it'll be easier to take those repeated derivatives. Then we're going to take these and replace all the x's by 2. I get 2 over 4, which is a half. I get negative 4 over 8, which is negative 1/2, etc., etc. So remember, the numerators of the coefficients are these numbers right here. So our Taylor polynomial of degree 4 is f of 2 over 0 factorial x minus 2 to the 0, but x minus 2 to the 0 is 1, 0 factorial is 1, plus the first derivative at 2 over 1 factorial times x minus 2 to the 1, plus the second derivative at 2 over 2 factorial times x minus 2 squared, third derivative, 3 factorial, power 3, fourth derivative, fourth factorial, power 4. And these guys here, these numerators of these coefficients are what we found over here. So we'll just plug them in. F of 2 is 1/2. F prime of 2 is negative 1/2. That's over 1 factorial times x minus 2 to the 1, etc., etc., etc. Now later they're going to say, okay, now that you have this Taylor polynomial of degree 4 near 2, use it to approximate, for example, f of 2.06, which is near 2. So you'd be able to go into this polynomial, replace all the x's by 2.02, and get a good approximation. Okay. A different and easier way to do numbers 5 through 8. Remember when they said they wanted to agree everywhere? Way easier to just do it with the table. It's degree 1, so you're going to go 0, 1. Your original given function is 4x to the negative third. The derivative of that is negative 4/3 x to the negative 4/3. It was near 8, so replace x by 8, and you'll get 2 and negative 1/12. Whoops. I haven't seen that in a long time, have we? Okay, so we end up that our function near 8 is approximately equal to this Taylor polynomial. So there's the numerator. It's over 0 factorial times x minus c to the 0. which is 1. And then here's our numerator of which our f prime of 8 is here, negative 112 over 1 factorial times x minus c to the 1, or x minus 8. And therefore, you get this answer right here, which is a lot easier than what we did when we didn't have all the formulas. Okay, so just to point out again that numbers 13 through 24 are Maclaurin's, which means your C is 0, whereas 25 through 30, it's an nth degree Taylor polynomial they want, and therefore they have to give you the value of C.